It's on. Yeah, thank you very much. It's a great pleasure to be here at this great campus and this great conference. So actually, before I start my talk, I'd like to draw your attention to something very distressing that happened a few months ago. So on the campus of Posets University in Istanbul, we have had this research center called IMBM, which has been functioning for the last 15 years, and it was arbitrarily shut down. The story is long and complex, but then this is a straight off assault on academic autonomy and the ability of academics to do their own research. So if you want to know more about the story, you can check out one of those links over there. And the IMBM administration has also requested that you might consider labeling one of the seminars at your own institution as a IMBM seminar. So please take a look at this, and we'll be very happy for your support. Right. So this is a talk. I'm going to be talking about a basic class of posets, the so-called fence posets. Actually, there was a poster on this last year by Bruce Sagan and I'm sorry, I forget the other authors. There was Clifford Smith and there was I forget. But then they raised this interesting problem. It is easy to state, easy to understand, and it has a satisfactory resolution. So it deals with these fence posets and their rank polynomials, and it asks whether they were unimodal, and it turns out that that is indeed the case. So what are these fence posets? These are a basic class of posets. So I have a base set, and in this picture, I look at these base elements, and an up arrow means that x1 is less than x2, and a down arrow means that x3 is bigger than x4. Now, you start off with a composition, alpha 1, alpha 2, alpha s. So alpha 1 will be the number of segments in the first collection, and then alpha 2 will be the number of down segments, alpha 3 will be the number of up segments, and so on and so forth. So this gives you a poset, and let me give you an example. Concrete. Well, okay, this is the poset. This is the poset 2113. So this poset is not ranked, but what we will be interested in the lower ideals of this poset. So a lower ideal. So I will use ideals for lower ideals. So there's a down closed subset. So if you look at this example, we look at subsets that are closed under, downward closure. And for instance, there is one ideal of rank 0. If you look at ideals of rank 1, so that's an ideal of rank 1. Here's one more, and here's one more. So there are 3 ideals of rank 1. When it comes to ideals of rank 2, that's an ideal of rank 2. And if we continue, we will see that there are 5 ideals of rank 2. And then the full rank sequence. So if you list the ideals of various sizes, this is what we call the rank sequence. Or we could also encode this as a polynomial, which we call the rank polynomial. And well, it's certainly, the first thing that should strike anyone who's working combinatorics is that it looks very unimodal, right? So this was indeed the conjecture that was posed 3 years ago or so. And the context is extremely interesting. So this is one of the very lovely thing that if you haven't seen, you'll be delighted. So Morier-Genoud and Ovsienko, they introduced this very interesting q-deformation of the rational numbers. I'll be quick about this, but then the initial construction, the other constructions now, but the initial construction proceeds in the following way. There are 2 well-known ways of, 2 well-known continued fraction expansions for any rational number. This one is maybe a bit more classical. So this is a bit more classical. So all these A1 is an integer, and A2, A3, and so on and so forth are bigger than or equal to 1. There is one more that is slightly less known. In this case, all these integers are, so the first one is an integer, and all these other integers are bigger than or equal to 2. What Morier-Genoud and Ovsienko did is that they pulled this out of the hat. I believe there is some reason why they did this, but then they defined the q-deformation of. By the way, I mean, you can't define the q-deformation of a rational number as being the ratio of the q-deformations because that's not correct. It doesn't. I mean, 2r by 2s would have a different q-deformation. So what they did was they pulled this formula out of the hat. So they replace these numbers that arise in the continued fraction expansion in the following way. You replace a1 by its q integer, a2 by its q inverse integer, and so on and so forth. And then in the numerators, instead of 1, you put a q to the power of a1 here, q to the power of minus a2 here, and so on and so forth. So the expression when you look at this other continued fraction expansion is a bit easier to understand. But then the nice thing is that these two things agree. So you get the same expression for both of them. And also, what is very nice is that this object that you see over here, it's going to be a ratio of two polynomials with integer coefficients. This is straightforward to see, but then you get the same expression from both these continued fractions. And Morier-Genoud and Ovsienko, one more thing, when r by s is positive, then the coefficients are all non-negative. What Morier-Genoud and okay, maybe I should give an example here. So if you start off with 32 by 9, you write down this continued fraction expansions, and then you plug in these numbers, and you get the following expression. One important thing is that the numerator polynomial does not just depend upon the numerator. It's a function of both the numerator and the denominator, and similarly for the denominator polynomial. What they observed that in all the cases that they computed, both the numerator polynomial as well as the denominator polynomial are unimodal. They simplified the problem. I mean, they gave many equivalent expressions for these things. One of them involves these fence posets. So in this case, when you look at 32 by 9, it turns out that the polynomial that we saw on the last page, it's the ratio of two rank polynomials. This is the rank polynomial for 2, 1, 1, 3, and this is the rank the denominator that we saw over here. This is the rank polynomial. The denominator is the rank polynomial for a different fence poset, in this case, 1, 3. Yeah. In general, this is true. So what you can write down is that if you look at the standard continued fraction expansion, and then for r by s, then you can indeed write this down as the ratio of two rank polynomials that are related to this expression in this following simple way. Right. Good. Now, here are some examples. This was their conjecture. And so, the conjecture becomes the unimodality for fence posets, rank polynomial fence posets. So here are some examples. I'd like to draw your attention to a couple of things. So if you look at these numbers, there is, they're not necessarily symmetric. So in this particular case, it is symmetric, but they're not necessarily symmetric. And the other thing, but one nice thing is that the peak of the unimodal sequence, so the peak must occur somewhere. The peak always seems to be at the middle, but if the number of, so this thing, if it is, if n is odd, if you take a look at it, the peak would occur either at the ceiling of n by 2 or floor of n by 2. So there is some subtlety that is going on over there. So this conjecture was popularized by a few authors, including Bruce Sagan, who talked about it, wrote a couple of papers on this. Well, it's a very nice, attractive, easy to understand problem. But then what is even more nice is that you sit down and start making calculations and then you realize this may be, I don't know, it's frustratingly tricky. So fortunately, what they did was they came up with certain refinements of this conjecture. So these refinements, so okay, the base conjecture is that it is unimodal, but then there is this notion called a bottom interlacing sequence. So unimodality would just mean that A0 is less than or equal to A1 and so on and so forth. But bottom interlacing means that you have the following additional inequality. So AN is less than or equal to A0, which is less than or equal to AN minus 1, which is less than or equal to A1 and so on and so forth, right? And similarly, there is a notion of a top interlacing sequence. Both bottom and top interlacing sequences are unimodal with a peak, at the appropriate middle. This in the case of a bottom interlacing sequence, this in the case of a top interlacing sequence. So over here, you can check that for this particular sequence, 2, 2, 3, then it turns out to be top interlacing. Okay. So yeah, this is top interlacing. Maybe this should be bottom interlacing. I'm sorry. No, sorry, that's correct. Yeah, this is top interlacing. Right. So if you look at some of these rank polynomials, so in this case, you get in certain cases, you get bottom interlacing sequences. In certain cases, you get top interlacing sequences. In certain cases, they turn out to be, so if something is both bottom and top, then symmetric, right? But trust me, that, we spent a lot of time trying to figure out whether we can predict whether it's bottom interlacing or not. But it's a simple problem that, we spent much more time on it than we should have, but we still don't know how to do it. Okay. Right. So I'd like to, so this is the more refined conjecture. So not only, so they say that, so this is a systematic way of writing the conjecture. So you have a composition with S parts, okay? Then S is 1, meaning there's a single part. So you have a chain. In this case, the rank polynomial is very simple. Okay, this is so, okay, part A we have already proved. But then the conjecture says that if S is even, then you have bottom interlacing. If S is odd, depending upon the structure of the initial and final parts, so you have some structure. Okay, so this is not completely necessary because you'll get. I'll show you a flavor of what goes into the proof in a little while. Okay. So some comments. I'd like to make some comments about this conjecture. So these sequences are unimodal, but they are not. They are seldom log concave or anything. So this is somehow analogous to what we know for the Gaussian binomial coefficients. So they are often badly unimodal, right? So sometimes you can have long flat parts, right? So this makes using algebraic techniques challenging. As I mentioned, life would have been a lot easier if you could figure out where exactly the peak is, but yeah, there seems to be no way of figuring that out. Now, you can, within a few minutes, you can write down various identities. So if this is the rank polynomial for some composition, and then there are these recurrence relations between various rank polynomials, and you can write down half a dozen of them. Quickly. So this one, what I say is that, so the fences that I showed you, they start with the up step and the second step is a down step and so on and so forth. They can also start with a down step. So this is so meaning that the first step is alpha, the down step of alpha, right? Yeah, so you can write this out and then you can spend time, playing with these, but frustratingly, they, after a couple of weeks, you'll figure out that there's something extra that we need to do. Right. Another thing is that there is a nice interpretation in terms of quiver representations, and these things come up in the context of cluster algebras as well. So if you take a type A, I'll go a bit fast over this because it is not relevant to the talk. So if you have a type A Dynkin quiver, you look at indecomposable representations, and if you think about it for a bit, then basically these lower ideals, they are basically indecomposable representations. So if you rank indecomposable representations by dimension, which is the size of the lower ideal, then you have unimodality, for this sequence. Another nice thing is that this F alpha. So what is F? You have this this thing. So you have this fence poset, and you have the lattice of lower ideals. This F alpha, it comes up in many contexts. So in a paper, Prop, he introduced snake graphs, and you can interpret them as perfect matchings on snake graphs or lattice paths on snake graphs. Then there is this something called angle, which comes up in the context of cluster algebras. So you can understand these in terms of perfect matchings on angles, and there are these T paths, which were introduced in papers by Schiffler and by Hugh Thomas. And there are also these S paths, which were introduced in a thesis by Clausen, who was a student of, a graduate student of Bruce. Great. Now, actually, the thing is, there is one nice idea that actually, it's one of those things, it's the magic key. So the magic key is this, and then, it's all this is due to my collaborator Ezgi, who has this amazing thing of pulling things out of the box. So, well, one thing you can always do is actually inviting you. I mean, let's close up the fence. So in this case, there's a dotted line, which means that we are identifying the elements x1 and x8. Okay. So, or if you want, what you could do is, you could. I mean, there are many ways of of closing up a fence. We will see this, but for now, let us just. So this has the base set had 8 elements for the fence. Now, but you identify x1 and x8. So now you have a fence. Now you have some poset with 7 elements. Great. And then if you compute the rank sequence, then this is very satisfying. This turns out to be symmetric. And one of the problems in the original problem was that you don't have symmetry. That would have made life a lot easier. But in this case, you do have a symmetric rank polynomial. And well, initially we thought that this was some coincidence, because actually there is, think about it. I mean, there's no real obvious reason why it should be symmetric. And we computed lots of examples, and yes, it turned out that it is indeed symmetric. And what is even more interesting is that it is not, I mean, you would expect that there's some very easy way of just flip the fence upside down or something, but it is not the case. It turns out to be symmetric, and the proof itself is, it's not trivial. So this observation, was a crucial component in our proof. Closing up the fence and showing that, seeing that circular fences, they have the symmetry property. Right. So this thing, en route to the main theorem, we proved the following thing. This has some interesting follow-up consequences, which I will mention. So the high-level idea is that, okay, you want to show that it is symmetric. Okay, I mean, one thing that you could do is, okay, if you have something like this, if you have a composition like this, then it's actually quite easy to see that you do have symmetry by just flipping up and flipping left. And then let's try to take any composition and try to bring it to this composition. So which means that, what we do is, we try to move a base element from here over, a peak or under a valley. And then, there is a calculation that is required. I mean, so there's a 2-step induction that is required. It turns out that is indeed the case. And then, so the idea is that, we show that this thing does not break symmetry. If this were symmetric to begin with, what we get is also symmetric, and then we end up with something symmetric. And so that's a high-level idea. Now, why is symmetry helpful? By the way, I should mention that this thing, actually, we spent a lot of time trying to find a bijective proof, and Bruce Sagan and Sir Elizalde did give a bijective proof, but then the proof is not trivial. The proof is quite subtle, and we don't know of a simple proof. Yeah, great. So now the other thing is that, I'd like to mention a couple of, so you could identify vertices to get a circular fence, or what you could do is you could add, in this case, you're adding a relation, x1 is bigger than x8. So then again, you get a, so if you, I mean, what x1 is bigger than x8 is roughly what you're saying is that you put a vertex below this and then you identify this. Yeah. Now let's see what happens in this case. So if you compute the rank polynomial, of this original thing, there are 2 things that could happen. So you have, let us look at ideals. Do I have an animation? Yeah. So let us look at ideals where this one belongs to the lower ideal and this one does not. Okay. So which means that, this thing would be illegitimate in the circular fence. But then everything else is legitimate. So where neither of them belong, both of them belong, or this does not belong and that belongs. Okay, those will, so these things, so this case would correspond to this object. This case would correspond to the rank polynomial of a circular fence, right? Which we know. Okay, let's assume for now that it is symmetric. Okay, we're not assuming unimodal, just that it is symmetric. Okay, then this one, however, if this object, belongs, this object does not belong, right? If this does not belong, none of these can belong. So this means that this is actually the rank polynomial of a smaller fence poset. And this thing, if you, there is one thing, it's smaller, but also what you have is, we are putting this q in. So this is a rank polynomial of smaller fence poset. And then you have a q, you shift it slightly. But let's see what happens in this case. So in this case, so you have a symmetric piece. and then you have a piece that is smaller, that is shifted by one element. Okay. Now, in this case, because of symmetry, we have these relations. Okay, we're not assuming unimodality. In this case, so we use induction, plus the fact that the shifting does not, shifting will not make things bad. One can check that. And so you will have these following inequalities. And if you put them together, you get these inequalities. Okay. Now, these are precisely, when you look at bottom interlacing, these are 1/2 of the inequalities for being bottom interlacing. Okay. So we get half of them. And yeah, then, but for the other half, what we have to show is, so we also have to show that this A0 is less than or equal to AN minus 1. So these things we have showed. Even, the even things we have showed, the odd things we have to show. And for that, what we do is we associate a different circular fence. Okay, we associate, we add a new vertex, x0, and then we close it up appropriately. Okay, and then in this case, you will get a relationship in which this is a circular rank polynomial circular fence with symmetry, and then you're subtracting something which corresponds to a rank polynomial of a smaller fence, right? And then if you work this out, then you have exactly the other half of the inequalities that you. I mean, it's all very pretty, but it's sort of it works, and but then yeah, we had no idea it would when we went down this route. Now, so once again, so you have this thing, so you have this theorem that tells you that you always have unimodality, plus you have some refined versions of unimodality for appropriate fences. So this says when it's bottom interlacing, top interlacing, and so on and so forth. Now here, there's one thing I'd like to tell you that if we knew that these circular fences were symmetric, then life would have been easier. But that actually there's a sort of a two-step induction. So we go from unimodality of fences with at most n parts to showing symmetry for circular fences with n plus 1 parts, and then we deduce unimodality with n plus 1 parts. But then this actually should ask, there is a natural question, what about circular fences? Do we have unimodality in that context as well? It turns out not always. So here is an example. So if you take a circular fence or the form 1A, 1A, then it's almost unimodal. You have a dip in the middle. Okay. And showing unimodality was actually surprisingly hard. So this thing, I mean, hard in the sense that, I had to burn a lot of midnight oil, but eventually, I mean, not in the original paper, but in a follow-up paper that we'll put up soon, we were able to show that this is true as well. So apart from this one parameter family of cases, we do have unimodality in the circular cases. So do I have 5 more minutes? 3 minutes, great. So I'd like to mention a very interesting context, in which this comes up. So if you look at Young's lattice, and now you can look at generating function for all partitions that lie inside a given Young diagram. Okay. We can also look at, you fix 2 Young diagrams, one contained in the other, and you look at things in between. Now, what we have is, I mean, do you have unimodality in this context? So let's assume things that lie inside a fixed Young diagram. It turns out that not always. So I'll give you this example. Yeah. So if you look at this thing, if you look at a Young diagram 8844, it turns out that the generating function for things that belong to 8844 are not always unimodal. There's a dip in the middle. This dip does not occur at the exact midway point. Okay. But then there is this famous conjecture that many people have thought about, that if you have a self-dual partition, then you should have unimodality. Yeah. Now, there has been, some follow-up work. So I will end. I'll just briefly mention that, the symmetry for Young fences, for symmetry for circular fences, can be seen in a. There is a nice polyhedral perspective that gives you an infinite family of non-isomorphic polytomes with the same Erhard quasi-polynomial. And the other thing is that there has been some follow-up work in terms of there is this interesting deformation of the SL to Z introduced by Leclerc and Morier-Genoud, and there are a couple of conjectures concerning unimodality of some natural polynomials that arise in that context, and there has been some follow-up work concerning that as well. So I'll take the opportunity to end here. Thank you.
Questions? You said these polynomials were barely unimodal, didn't have any stronger property. Could you quantify that in any way?
No, all I was saying is that that there are you can have, depending upon the the fence, you could have long flat segments. So I mean there are examples where it increases.
Okay,
there's a
so
long.
there is no you can't think of anything stronger than that, obviously, because of that.
Nothing that is, widely considered. I mean, there may be some exotic properties, but like those Gaussian binomial coefficients, yeah. I mean, there may be some exotic versions, exotic strengthenings.
Which of the posets might be not from Plane?
Yeah, I mean, yeah, I mean, I think it's one of those things where I don't know. I don't know if that's a natural question to ask, but yeah, one could run some computer experiments. Sure.
Do you know if these rank polynomials for different fence posets, whether they'll be different? Or like, for example, for even if you flip the composition, I mean, you'll get the same rank polynomial, but are there other cases?
Correct. So there are some weird coincidences. Yeah, it's very weird. I mean, I don't know if there is a pattern to this, but yeah, we looked at what happens with 4 parts, and there are some non-trivial equivalences, but I don't know. I mean, does it mean anything? I don't know, but yeah, it's worth looking at it. Sure.
Okay. Well,